Alright, now that we have studied how to connect capacitors in series and parallel, let's look at a more complicated circuit where you see both of them appearing simultaneously. A simple example of this so-called more complicated situation is like this. It's got 1, 2, 3, 4, 5 capacitors. It's actually not that complicated. The idea is we're going to start from a smaller part of the circuit. You see, first of all, these two things are in series, right? They're one right next to another. So we can combine that first, and after that we can then combine with this guy, which is connected in parallel with the two. Then we get the equivalent of that part, which then should be connected in series with this guy to get a certain equivalent capacitance for the whole upper branch, and then you combine them in parallel with the lower branch. So you see, the idea is to start from a smaller part and gradually include bigger and bigger part of the circuit until you get the entire circuit covered. In this particular case, let's for simplicity assume all these capacitors are equal in value. They're all equal to C. Okay, so let's combine these first. These are in series, so we got 1 over C plus 1 over C, right? And you flip it over. As a matter of fact, you just get C over 2. Okay, it is clear from very simple algebra. If you have n capacitors, identical capacitors in series, each has a capacitance of C, then the reciprocal, the sum of the reciprocals will be just n over C, right? And you flip that over, just C over n. So in this case, n equals 2 because there are two capacitors in series. So it's just C over 2. Now, C over 2 plus that guy in parallel. When they're in parallel, just add them together, right? So it's half of C plus C. So that's 3/2 of C, okay? 3/2 of C, which we connect in series with this guy, okay? So how does that work? Well, you have to take 3/2 of C, flip it over, plus 1 over C, and then you flip it over, okay? So it's something like this. And you flip it over, okay? That'll give you C of this upper branch, right? You can easily work that out and see what you get. And then once you get that, how do you combine with the next branch? Well, that is in parallel with the next branch, so all you have to do is add another C. Add another C. That would be C equivalent for this particular setup. And there are only 5 capacitors in there. I can add 10 more if I want to, but as long as every segment of the system can be broken down into series or parallel, I can always start from a smaller part and gradually include everything. Okay, but is it true that whatever the connection among a bunch of capacitors, one can always break them down into either series or parallel, or maybe the combination of the two? Well, let's take a look at the next example. What about that? Okay, so what do we have here? We have again 5 capacitors, but they're now connected like this. 1, 2, 3, 4, 5. There is an upper branch and there is a lower branch, but interestingly enough, in between the upper branch and lower branch, there is a 5th capacitor which acts like a bridge, okay, between point C and D. Now, if this bridge does not exist, what is the equivalent capacitance? Well, that should be a piece of cake. Suppose each of them has the same value C, okay? Again, you first consider the upper branch locally, and you just get C over 2, right? And the lower branch also C over 2. And then what do? You simply add C over 2 and C over 2, you get C, okay? So these 4 capacitors without the middle one will simply add up to an equivalent capacitance of C, okay? Now, what if I add a 5th one? Well, think about it. Before you add a 5th one between point C and D, this C and that C, due to the fact that they have the exact same capacitance, you know that whatever voltage difference between A and B will be equally shared between this capacitor and that capacitor, right? Because they have the same Q, right? So they're connected in series. They have the same Q, and then they also have the same C, and therefore Q over C is also the same, which means V1 equals V2. Similarly, V3 equals V4. Okay, so let's look at some numeric example. Suppose this is 0 volt and this is 12 volts. Okay, so you have a total of 12 volt voltage difference between these two and between those two. and that means each of them gets 6 volts, okay, of voltage difference. So therefore, if you have 0 volt here, what is the voltage? What is the voltage at that point? That would be 6 volts, right? And the voltage at point A would be 12 volts. So you have a 6 volt potential difference across these two plates and 6 volt potential difference across those two plates. So again, point C would have a voltage of 6 volts. What about point D? Well, if these two have exactly the same capacitance, we'll have the same deal. This will be 6 volts, this will be 12 volts, and that tells us that point C and D have the exact same voltage. Okay, they're at exactly the same level of electrical potential. Now, if that is the case, then what happens when I connect this capacitor? Would anything happen? Will this capacitor be charged? Well, it won't be, right? Because the voltage difference across the two plates of this capacitor will be 0. Okay, so a capacitor is there to store some charge so that it can have a potential difference. But there is no potential difference in this case, so the capacitor does not carry any charge. If there's no charge flowing onto it, then this capacitor is totally useless. In other words, even after we connect a capacitor, a fifth capacitor here, nothing happens. Okay, so if all these are the same value C, then the equivalent capacitance of this 5 capacitor setup would just be C, as if the fifth one does not exist. And you can even extend this result beyond the simpler case when all these C are the same. What you really need to do is to make sure points C and D have the same exact voltage. Okay, and that does not necessarily require all these C's to be the same. All we have to make sure is that if this C1, C2, C3, C4, all I have to make sure is C1 over C2 equals C3 over C4, so that if let's say this voltage here and there's a ratio of 3 over 2, all I have to do is make sure there's the same ratio of 3 over 2, so that point C and D have the same voltage. Okay, under these circumstances, the fifth capacitor is not really useful, so I can ignore it when I calculate equivalent capacitance. But of course, things may not always be that simple. The most general case, C1, C2, C3, C4, and C5, let's say they're all different, and there is no such relationship C1 over C2 equals C3 over C4. Now what do you do? Well, can this be simplified as some sort of equivalent series or parallel connection? Well, without this fifth capacitor, these guys are in series, those guys in series, and these two branches in parallel. Okay, do you think this fifth guy is connected in series or in parallel with anything else in the circuit? Well, some might say that if you start from this capacitor here and you branch out, you see it branches out. Looks like C2 and C5 are in what? Are in parallel because they branch out. But the thing is, if two capacitors are in parallel, okay, we have to make sure that they do not only start from the same point, like point C, they split out into two branches, but they have to come back. Okay, they also have to come back to the same point at the other end, and in this case, do they come back? Okay, C2 goes to point B, but C5, you see, goes only to point D, and before it can reach point B, you have to put another one here. So C2 and C5, they're not in series. I'm sorry, they're not in parallel. As a matter of fact, this is an example of a case where you cannot really break down this circuit into a bunch of series and parallel connection. The fifth one is connected neither in series nor in parallel with anything else. So what do you do? Okay, if it's series or parallel, we can always, use the formula either in series or parallel. But if that is a more it's a more complicated case, then if everything else fails, we go back to the basic. Okay, what is the basic? How does one define an equivalent capacitance? Okay, when define equivalent capacitance, if I can replace this whole setup between points A and B with a single capacitor, which will produce the exact same capacitance as this combination. In other words, if I connect these 2 points A and B with such a capacitor, okay, we call it C equivalent. Then this capacitor hooked up to a certain voltage, okay, just like here, hooked up to the same voltage, same battery. These two setups would produce the exact same amount of charge connected to point A, same amount of negative connected to point B. Okay, that is the meaning of equivalent capacitors. Now that tells me that if you add all the charges connected directly to point A in this setup, it should equal to this Q here. Now, how many plates are connected directly to point A? Well, it will be this plate and that plate, right? So let me call this charge Q1 on the left plate of C1 and Q3 on the left plate of C3. Then Q1 plus Q3, that's the net charge connected directly to point A, which is connected to positive terminal of the battery. And then over here I have only a single amount of charge Q directly connected to positive terminal of the battery, and these two are equivalent, and therefore we say Q equals Q1 plus Q3. Okay, now next, if this is Q1, then that got to be negative Q1. That's from Gauss's law, and that's got to be negative Q3. What can we say about the charges on C2? Is it necessary for this to be equal to positive Q1 so that it cancels with this? Well, remember, if you look at plates 1, 2, and 3, these three plates, initially what's the total charge on them before the battery was installed? Of course that's 0. There's no charge on any plate, right? Now, after you install the battery, some of these plates will be charged. In fact, all the plates will be charged. But if you look at this combination, okay, consisting of, again, plate 1, 2, and 3, as a group, they were actually isolated from the rest with only air gaps, right? So what is the total charge on all of these three plates? This one, and this one. Well, it was 0 before, it has to be 0 now because nothing can come in and out of this group. So therefore, if this were equal to Q1, then with a minus Q1 here, that's going to leave no charge on the fifth capacitor. And we know, in general, that is not necessarily the case. So therefore, I cannot say that this has to be equal to positive Q1. Okay? We just call it something more general. We call it Q2. So this is negative Q2. And similarly, on this plate I have Q4, and here is negative Q4. Okay, now I have Q1, Q2, Q3, and Q4, but don't worry, we'll fix that. Alright, now, one of the things you realize is that this battery can only transport some charges from one place to another through its two terminals. Now we know that it took amount of charge Q2 and Q4 from these two plates and transported them to those two plates. Okay, how much charge did it take from these two plates? That would be Q2 plus Q3 plus Q4. That is Q2 plus Q4, right? And how much charge got deposited onto those two plates? That will be Q1 plus Q3. And you know they got to be equal. Okay, so no net charge is actually produced by the battery. The battery only transports the charge. It does not produce any charge. Again, how much charge is on this plate of C5? Well, this charge plus this charge plus this charge is 0, and therefore on this plate I must have Q1 minus Q2. What about this guy? What about on this plate? That will be what? You have a Q4 here, a negative Q3 here, so that must be Q3 minus Q4. Okay, and you can see, you can show easily that the amount of charge on this plate and the amount of charge on that plate have equal magnitude and opposite signs because of this formula. Okay, so now assign all the charges on each plate of every one of these 5 capacitors. But I end up with four unknowns, Q1 through Q4. Again, my job is to find Q1 and Q3 as a function of V, okay, as something proportional to V, so I can take the ratio of C equivalent, and that's just Q over V by definition, Q over V, which is equal to Q1 plus Q3 divided by V. So I need to find Q1 and Q3 as a function of V. Okay. So what's next? We have to establish new equations which help us find Q1 and Q3 both as functions of V. How do we do that? Okay, how do we do that? Well, the idea is quite simple. You see, as you go from the negative to the positive terminal, okay, you can go through any path as long as you go from point B to point A. How much should the change in voltage be? Well, it must be equal to V, right? Okay. Now, suppose I take a path like this, the top path, okay, that takes me from point B to point A. I will encounter these two capacitors, and each time I encounter a capacitor, the voltage changes. In this case, it went from negative to positive terminal, the voltage increases. Again, going from negative to positive terminal, the voltage increases. But you add the change of these voltages. You add them all together, you're going to get V. Alright? So let's look at the top branch. I have, first of all, the voltage increased from here to there by how much? Well, the charge is Q2. The capacitance is C2. Therefore, the change would be V2 equals Q2 over C2. So I have Q2 over C2. That is the voltage increase going from this plate to that plate. And you go to here without changing the voltage, and then when you cross this air gap, the voltage increases again. By how much? By Q1 over C1, right? And guess what you get? You get the voltage at that point, which is a value V greater than that. Okay, so the voltage difference is V. So that equals what? Equals V. Alright, now you get the idea. Suppose I take another branch, right? Take the lower branch. What do we get? Well, we get from here to there, it's Q4 over what? C4, right? And then from here to there is Q3 over what? C3. That also gets you V. Okay? So let's see how many equations do we have now. I'm looking for Q1 and Q3. I'm looking for Q1 and Q3. So I need equations. I have an equation here, here, here. Okay. I have in these three equations. Okay. In these three equations, I have four unknowns: Q1, Q2, Q3, Q4. But I only have three equations. So I'm still missing one equation. All right. But not to worry, because I haven't touched the fifth capacitor yet. So I'm going to take a path which goes through the fifth capacitor. Alright, so instead of going this way or this way, is there any other way I can go from point A to point B, passing through C5? Well, why don't I go this way? Hey, go this way. I can do that, of course. So, how do I do that? First of all, I go from here to there, and then I get Q2 over C2, right? Which gets me here. Okay, which gets me here. Now, I don't know which one of these is positively charged, which one of these is negatively charged. Okay, but let's make an assumption. Let's say this plate is positively charged and that plate is negatively charged. If that is my assumption, then as you go from here to there, the voltage should increase, right? By how much? By an amount of charge here divided by C5. All right. If my assumption was wrong, then I will get a negative sign in both Q and delta V. So you know it actually cancels out. So all I have to do is to be self-consistent. So I'm assuming again this is a positive charge and that is a negative charge. So the positive charge is Q3 minus Q4. So Q3 minus Q4. That is the charge on this plate. You divide it by C5. What does that get you? That gives you the voltage increase as you go from here to there. See, the voltage should increase because this is positive, that is negative. Then we'll arrive at point D. Once you're at point D, what do? You keep on going this way until you reach point A, right? So again, you add another term. This is Q3 over C3. So you went this way, this way, this way. You arrived from point B to point A. So again, the voltage difference is V. Okay? So now you have four equations. 1, 2, 3, and 4. In principle, we can solve these four equations. So we will get Q1 through Q4. We don't really need all of them. We just need Q1 and Q3. You put them together. Both will be directly proportional to V. So you take the ratio, you will get C equivalent. Okay, I'm going to leave this as an exercise for you to finish the rest of the algebra. You can find C equivalent as a function of C1 through C5. And in particular, you can see from the formula that you get that if C1 over C2 equals C3 over C4, then your formula just goes back to something totally expected, and that is the equivalent capacitance without C5 involved.